Okay, so it's 2 minutes to 3 p.m. But since no one has joined yet, I'll wait for a few more minutes and we'll get started with today's content. Okay, so it's 3 p.m. already. Hello and welcome to this week 12 TS session on optimization methods for civil engineering. Since this is the last class of this course, so today, since no one has joined yet, I'll wait for. Okay, so I have one person join. Okay, since no one else has joined yet, I'll wait for a few more minutes and we'll get started with today's class. Alright, so I'll get started anyway with today's content. Hope people will listen to this later on. So, welcome to this week 12 TS session on optimization methods for civil engineering. So, since this is the last class of this course, so I wanted it to be a bit interactive so that people could ask questions and so on. But since no one has joined, I'll just go ahead with the content that have been taught in this week, and mostly that's related to the programming side of it. So there are few examples on R, MATLAB, and then Excel to solve optimization problem. So I won't be going into the details of like those real life design problems that Sir solved in the class, because that's kind of too domain specific. I felt like whether you're structure students and water resources students probably will be understand it better. So anyway, I'll just in general discuss those problems that have been already discussed in the class. So first I'll look at some of the examples of R that have been already given in the class, and then I'll just solve a couple of problems also that is there in the assignment. So similar type of problems I'll solve. So that's the plan for R. Then in MATLAB also the optimization that have been taught, mainly the particle swarm optimization and genetic algorithm. That part I'll just cover and then just solve one or two problems in Excel. So that will be all for today's content. So the first problem is on this differential evolution, and the theory of it you have already seen in the hello yeah, I'm Trix. Oh yes. Okay, so I think yeah, it got recorded, but through my other microphone. But yeah, sorry about that. My mic was muted. So this Google Meet thing. Yeah. So yeah, thanks about that. So I was talking about the content that I'll be covering today. Mainly it was on R, MATLAB, and the Excel optimization part that have been covered in the class. I won't be going into the details of the design problems that have been solved in the class. I'll just look at some of the other examples that have been covered, and also similar problems which are there in the assignment of this week. So let's take a look at this differential evaluation problem using this R programming. So the function is given as x1 minus 2 whole square plus x2 minus 1 whole square, and it is subjected to a couple of constraints. So we can solve the unconstrained version of this problem using differential evaluation, and then you can also solve it by adding those constraints, and then you can run your d-optim function. So let's just quickly go through this since you have already seen this. So this part, so you have to install this package, which is d-optim package. I have already installed it, so I can just import it here. And then this functions, the sequence function, outer functions, and this plotting and everything that you have already seen. So I'm not going into the details. So this is how your curves look like. So these are your level sets using those blue markers, and your constraints are shown using this green marker. So your optimal solution should be somewhere in this portion. So anyway, I can comment this part because I'm not solving the unconstrained problem. So let's solve the constraint problem. So here you have already seen that this is your objective function, and these are your two constraints, this G1 and G2. So if you satisfy these constraints, then it's fine. You can just have this as your objective. But if you violate that, you take a very high penalty for that in your objective. So this part you have seen. So let's run this part quickly. So this part is run. Now this d-optim function, it's just one line of function. You just pass your function which you are optimizing, and give the lower bounds and upper bounds of your variables, and that should solve your problem. So we're storing it in results. So this is the solution that you have got, which is 1 and 1. So this is the solution for the constrained version of the problem. Otherwise you would have got a solution of 2 and 1. So next you can just plot this point on this graph, and this is the red mark point, and the summary you can also see that 200 generations were used by default, and best solution is best member is 1 and 1, and best value is 1, and this function was evaluated 402 times. So this is a simple problem. Another problem is also similar. So you have just a different function here, which is an unconstrained function, and everything else being the same in this problem. And yeah, the constraint structure is different, but you have to have this linear constraints here. And you can solve this problem using DOptim package. So I'm not going into the details of it, because since it's almost the same thing. So here, this is how your level sets and your constraints will look like, and your optimal solution should be somewhere here. So let's run the constraint function, then this DOptim function. So after this 200 iterations, you got your solution as minus 0.2 and 4.4, and then you can just plot these points, and then what you can do, you can check your summary. So that's again pretty similar. You got the solution from here, and then your objective function value from here as well. Alright, so let's look at another problem, which is something a bit different from the previous one. So no, this one is also like same problem. It's just the constraint optimization with multivariable function. So this is how your function structure looks like, and you have just one constraint here. So let's see how it looks like. So you can run this, and this is how your constraint and level sets would look like, and your solution should be somewhere here. So it's again just writing the function and adding those constraints, then running the DOptim package, and again it ran for 200 iterations, and after that it stopped, and your solution is 0.2 and 1.6, and this function value is 9.8, and you can see that the point is somewhere here, and also you can check the summary. So the summary gives you this 0.2, 1.6 and 9.8. So these three were same type of problem. Let's see the next one. So next one is this different problem. So this is solved using this NSGA 2R2 package. So this is the NSGA 2 example. So again, you have to install your package. I have already installed it, and you can just import that library. So you can run that, and then the function that was given was so this is for multi-objective function optimization. So since it's a multi-objective genetic algorithm that you are using, so you will get some Pareto optimal front from this by solving this problem. And the function, the two objectives that are given is, one is x1, so that's written here. The another one is 1 plus x2 square minus x1 minus this a sine b pi of x or x1. So this a and b values are given, which is 0.2 and 1, and then it's pretty similar to the previous problem. Here also you need to run just one line of code, but you need to be careful that so you have to pass these arguments. So you will pass your objective function, which will be a multi-objective function. So we have this f1 and f2, and I have row binded that function. So that has been like stored in this obj fun, and then how many input parameters that you have, how many output parameters that you have. So you have x1 and x2, so that's why it's 2. You have f1 and f2, that's why it's 2. And then you would give your lower bounds, which is in this case 0 and minus 2 for x1 and x2, and upper bound is 1 and 2. And then you can use some population size, you can define it as well. So if you run this, then you should get your results stored in RES, and then you can plot it and check how the Pareto optimal front looks like. So let's run this. So first I'll import the function, then I'll just have this a and b values, then I'll run this obj fun. Let me clear everything from here, otherwise let's run this part again. Yeah, next is you just get this function stored in this obj fun. Then you can run, and your results are stored in RES, and then you can plot your Pareto optimal front, and it will look like this. So let's say I change the population size to 100. Then you will get lesser number of points on your Pareto optimal front and so on. So if you use a high value, so 700, yeah, you will get like more points here in this front. So this is how your this plot looks like, and let's see how this RES looks like. Okay, so it has, yeah, some information, I guess, about the points that you have evaluated. So I think these are the points, and I think this is related to some yeah, so 200 rows were omitted, so that's why there are 500 being shown here out of the 700. Okay, so anyway, so you are interested in the plot, so you have got this plot. So let's move on to the next problem, which is again pretty similar to this one. Here also you have a similar kind of problem, but now you have 3 functions. So you are optimizing for 3 functions, and for plotting that you need to have this 3D plot kind of a view. So that's why you need to install this plot 3D package, and then you can import those libraries, and then you can just have those objective functions written, different objective functions, f1, f2 and f3, and finally you can run this your NSGA2 algorithm. So now you have 2 variable inputs, so x1 and x2, but you have 3 outputs, which is the 3 objective functions, f1, f2 and f3. So that's why this is 3. And similarly you have this lower bound, upper bound, population size, and some generations you can also specify. And then I'll be plotting this in a 3D plot, so that's why I took all the values from this RES and took the x, y and z, or x1, x2, x3 coordinates and plotted those, and the levels and those theta rotations and everything are specified here. So let's run this one by one. So first I'll import this libraries, then this function is run, then this RES is run, and then this plot will look like this. So this has been also been shown in the class. So this is how you can visualize your plot in this using this plot 3D. And this will be your Pareto optimal front in this case. So those points are, if you pick any of those points, that will give you your solution maximum objective value. So in order to like optimize for multiple objectives. So now let's go for the final problem that was discussed in this module. So let's quickly go through it. So let me, okay, I'll clear it later. So the problem is again similar. Now you have 2 objectives that you have, x1 and 1 plus x2 by x1. But the thing is that now you have constraints. So you have this 2 constraints that have been written here. So you have to define another function, which is constraint function, which have been written as confun here. And then similarly you can do rbind and store those 2 constraints in this confun. So here the only difference is that you have to pass this extra 2 arguments. So this constraints equals confun, and this c dimension is the number of constraints that you are using. So here it's 2, and then the rest of the things are pretty similar. So let's run this again one by one. So you now first store objective function, these are your constraint function, you run this RES, and finally you plot the Pareto optimal front, and in this problem it will look something like this. So let's use this 600, maybe I can have just one constraint. And let's try this. Anyway, won't matter, I guess. Okay. Let's see if I can run this. Okay, so now the plot looks something similar, but this y-axis values got changed, I guess. Yeah, so depends on how many constraints you have. You can add multiple constraints or remove, but depending on the number of objective functions you have, you need to be careful whether you need to do a 3D plot or some higher dimensional thing, but you cannot visualize those things. So you can visualize up to say 3D in this case, so you can have 3 objective functions and check, but you can solve the problems for multiple objective functions, even more than 3 as well. Okay, so this was all about the discussion that was there in the class. So I think there were a couple of problems related to our coding in the this assignment. So it's not the exact same problem. I made some changes to the values, but I think the code and everything was also given, so you just have to read the output, that's all. So it is pretty simple. So, and both those problems were on this doptim package. So let's first import this, then you have this function. So this is the 2 variable function that you have, and now this is the unconstrained problem that you can notice, and your upper bounds and lower bounds are defined. So and then you got this solution 0.79 and 0.31, and this objective function value is 1.4. so this you can do, and then you can do this summary, and finally what you have to report probably this x1 x2 values and also the function values. So it was pretty simple unconstrained problem, and the code was also given. Next was a constraint problem, but yeah, again the code was given. So here in place of f1 that we were using, the main objective function, here the fitness value is written. So it's the same thing, you can use f1 as well, not a problem. And you have your function as x1 minus 2 whole square plus x2 minus 1 whole square, and you have your 2 constraints defined, which is x1 plus x2 minus 2 less than equals to 0, and this x1 square minus x2 plus 2 less than equals 0. And again you do a similar kind of a check. So this whether if this constraints are satisfied, you take this as it is, otherwise you increase this by a very high number when there is constraint violation. And then you can just do the same thing within this doptim package. You can just pass your f, your lower and upper bounds of those variables, and you can get the summary. So that's simple. Let's run this problem quickly. So this is already imported, I'm doing it again anyway. Okay, yeah, so this is the value that you have got here. It's I think 0 and 2, and this is 5, and this the summary is like this 0, 2 and 5. So we can probably change something here. Let me do this as 5. I can, so it was 0, 2 I guess, so I can have this upper bound, it's 1. Let's run this. Now you got a solution which is 2, 1, and this best value is 10,000. So here I think what happened is that, okay, yeah, there was some issue, I guess. 2 plus 1, that's okay. Anyway, I think there is some issue here because this 2 plus 1 minus 2 is greater than 0, but I think since there was some constraint violation, so that's why this increment happened, and you got a output of 10,000. So probably your problem was not solved in this case. So let me make it 5 and check. Okay, I need need to just run this part. Okay, similar issues. Let's keep it as it is and check. Okay, yeah. Anyway, that should not have happened, I guess, because earlier I was getting a solution which was different. Okay, let's quickly okay, probably I changed the constraints, that's why this is happening, but yeah, it should not have happened. Okay, if it is 2 and 1, this is 2, this, okay, let's just do this. Yeah, now I got a solution, so let's keep it this way because I got a value of 3.79. So this was solved optimally and the members are 0.55 and 2.3. So anyway, the problem data that have been given in the assignment, you can put that and check for that, and similarly for the previous problem as well. Okay, so that's all about R and this differential evolution and NSGA 2 with R. So next I would go to MATLAB and just cover those basic optimization that have been covered in the class, those PSO and this genetic algorithm. So let me check. I don't think anyone has joined after that. Yeah, no one has joined after that. So yeah, probably this portion is too simple, and anyway coding won't come in the exam, so that's why probably people didn't join. So let's go to MATLAB. Anyway, let's cover everything. And I'll close R. Yeah, so these are again problems that have been discussed in the class, but let's go through them quickly. So let me comment everything which is below, and let's run everything one by one. So you have, first you have an unconstrained problem, so of a single variable, so that's why this x1 have been used only here in this case, and you could have just written in terms of x as well, so not a problem. And then you define your lower bound and upper bound for that variable, and finally you pass it to this particle swarm function, this objective function value, then this lower bounds and upper bounds and so on, and finally you store it this x values and the function values. So now in this problem, in order to run this particle swarm this function, I think initially you will get some error because you might not have your probably it is named as global optimizer package or something. So you will get a warning sign of that or error sign, so you can click on that and you can install it from there, and after that you will be able to run this. And also you can just probably go to this home and you can go to add-ins and get add-ons, and then you can just type the package that you want and then you can install it, and probably your MATLAB will be closed after that and it will again open once you have finished your installation. So yeah, be careful with that. So that's a minor thing. So let's run the run this for this particle swarm optimization problems. So yeah, so the solution, it's x equals 3 and this your function value is 27. So that's simple. I could change this values a bit and check what happens. Yeah, I got a different solution. So let's move on to the next problem. Again, it's the same as before. So let's run this. You have to probably comment this out. Okay, so what you have here, it's again a same type of function. You have function of one variable, so that's why here it's only x is being used. And you have this kind of a structure, and lower and upper bound are defined, so it's the same problem. You will get different values. So let's run the next one also. I think it is again a same problem. The function structure is different, but you have multiple variable now, so that's why you have to use this x, this first bracket, and this for x1 and x2 both. And since you were writing it in a factorized form, so in R it was square brackets, but here it's this curly brackets. And this now you have to define your this lower bound and upper bound. So this is a vector now. Earlier you were dealing with just a single variable problem, so that's why it's been written here. You could have used commas in between as well, but in MATLAB you may omit that. So even if you don't get problems like quoting anything in the exam, because the exam will be at an exam center, and I don't think there will be access to R or MATLAB or anything, but you should know the basic features of this uh, programming tools, both MATLAB, R, or even Excel. Probably you might get something small. I don't think you will get anything in Excel as well. Probably they will just allow you to use online that on-screen calculator that you have. That's all. And so probably problems which can be solved by hand, or smaller problems can be given, or like basic functionalities can be asked in the exam. So you need to know everything, what this every line does at least, because you could get problems like what will be the output of this portion. So you can just evaluate it on your own, and you have to probably enter that. So that's why you need to know the coding part as well. Anyway, so let's run this here. So the difference here is that here we were passing it as 1 for single variable. Now you have two variables, so that's why you have to pass 2 here. And now you can run this part. I'm not uncommenting everything which is before, but anyway, the final solution for this one is minus 3 and plus 3, and the function value is 2. So next is again a problem which is pretty similar. Here also the function structure is different, and this lower bound and upper bounds are given, and it's simple, same code. It's just a function that's different. So you can run that, and you will get solutions like this. So next is a function which has now this has constraints. So let's run this problem. So yeah, this is the last problem in this file at least. Okay, let's go through this one carefully, because it's a bit different from before. So here you define this your lower bounds and upper bounds. So you already know the usage of this once, and you are multiplying it by -5. So every value will be of -5, and this is the number of rows 1, and this is the number of columns. So you will get a row of 5 entries with -5. So that means you are dealing with 5 variables in this problem, which has lower bounds. Every one of them have a lower bound of -5, and the upper bound of each of them is +5. Then you store this fitness to fitness function. You just call this function ofun, and this is the output of the function, which is f. The input of that function is this x, which is a vector. And now this is your objective function. So this is an exponential function, e to the power say x1, x2, x3, x4, x5, and then minus of 0.5 times this, and the other terms that you have, x1 cube plus x2 cube plus 1 whole square. And then you have three constraints in this problem, so that also you can write inside the function. So it's pretty similar to what you have seen today in R. There also you write that f1, then you write g1, g2, and so on. So here it's c1, c02, or c03, and so on. So these are for your constraints, and you have written this constraint using this vectorized form, and then you have to again do what you have done in R, similar kind of checking. So if this constraint, so these are your equality constraints here, but you might get some less than equals to type as well, or other type of constraints. But there could be some issues with satisfying this equality type constraints. I think that was also mentioned in the class. So you can always use some sort of an epsilon and use less than equals to type constraint as well. So if all of these constraints are satisfied, your f, this is your say output, is equals to this objective function. Otherwise, if it is not satisfied, you are adding a very high 10 to the power say 185, very high positive number to it in case of constraint violation. So this is your function that you are optimizing. So this is a constraint problem, and then as before you have this res, which will contain your variable values, or x, you could have written it as x as well. This is your function value, and then you run that particle swarm function. You pass this one fitness function that you have stored, this function call you have made here. Then you give the number of variables, which is 5, then the lower bound of those variables and upper bound, and once you run this, you should get your results stored in this res and fl. So let's do that. Yeah, so your res is this 5 values. This is your solution, minus 3.98, so minus 4.88, and so on. And as I have already mentioned, so this is a minimization problem, and since this is an equality type constraint, so it's pretty hard to like exactly satisfy those constraints, because you are dealing with fractions anyway, and those must add up to 0. There could be some approximation errors and so on. Those things can always be there, and that's why here you are getting this objective function value to be that 10 to the power 185 because of those violations. So this problem can be handled differently as well by using some sort of a tolerance value that you can put to these constraints, and if that's less than equals to that tolerance value, that is satisfied. Otherwise you can put the high number. So there is that another way of doing it as well. So keep that in mind, that you are not getting the optimal solution from here by solving this. Okay, so let's move on to the next example. So let's comment this one. Okay, I have 1, 2, 3. Okay, 3 problems here. So anyway, since okay, let's go this one by one. Let's look at the first problem. It's the problem that you have seen before. It's again similar to that. Here your lower bounds are minus 50, and you have only 2 variables to deal with, and upper bounds of those variables are plus 50. Similar kind of function that you can write. The function structure is different, the constraints are different, and again, if you satisfy this less than equals to type constraints here, you have that objective function. So, otherwise what you do, you add this high penalty term, and the rest of the thing remains the same as we have seen in the previous problem. So let's quickly run it, and now you can notice that your function value is very close to 0. It's like 3.02 times 10 to the power minus 9. So and the solution value is 3 and 2. So here you get the optimal solution, or like there is some approximation error here, but anyway, that's as good as you saying that this function value is 0. All right, so so that's the advantage anyway of this dealing with this less than equals to type constraints compared to those equality type constraints that we have seen. Okay, so let's comment in this, because there are some issues if I don't comment it. Okay. because the function that you write should always be there at the end of your the script that you have. So that's why there would be errors. So that's why I'm commenting which is above this as well. Okay, let's look at the other problem. So this problem again, it's similar. It's just using different options for optimizing. So you have your lower bounds and upper bounds which are different. You are dealing with two functions. Again, you are doing the similar thing. You are having the C1 and C02, those two constraints, and you are doing similar things here. Again, you are using particle swarm optimization, but you are using the Sorn size and this hybridization and everything. And this hybridization is being done using that min-con function that we have seen in the previous class. So this hybridization means first there will be this particle swarm optimization being done. And in order to say avoid this kind of a situation where you end up at very near to the optimal situation, you do some sort of classical optimization from that point onwards to get to the solution. So that's the idea behind this one. So let's run this part, the entire thing that I have. Yeah, so here there is this tolerance values and all, using those options have been used, and you can notice that your solution is 0 and 1.5, and this function value is 8.5 exactly. There is no such approximation error and those things that you can notice here. So that problem is again pretty simple. So let's again comment this out. Let's look at this next problem. Okay, this is the first one. Okay, yeah, so this problem from line 42. Yeah, this problem is a bit different again, but here what you are doing is that you are using now genetic algorithm that you are using. And again, to define this constraints, we have already seen this in the previous class, that you can define linear constraints and non-linear constraints separately, or integer constraints, and then what you can do, you can define, say, this within that equality constraints and inequality constraints separately using this say coefficients or b coefficients that you notice. And this is the function that you have. It's a single variable function here, and you're doing the genetic algorithm and you're passing everything here. So you don't have any constraints in this problem. So anyway, that's the list is empty here. So let's run this. Anyway, I don't need to select. Yeah, so the solution was the same as we have noticed in the previous problem as well. So that's 3 and 27. So let's run the next one. Next is this problem. I think it's again a similar problem, so I think this one is also similar. Okay, so let's quickly look at all these problems quickly. So here also you have this objective function being defined. Then what you have, again you have some upper bound and lower bound being given, and everything here is also empty. So that's simple. The next problem is again those things, and everything else again being empty. So these are your unconstrained problem anyway, and the final one is also everything else is empty, and you are just solving that optimization problem, unconstrained version, whether it's a single or multiple variables. You're solving it using this GA library. So let's run this. Yeah, so after running this, only the last one is being showed here, but you can run the entire those things separately, and you can check that out later on. So that's all about this problem. Let's look at, I think there is a couple of more problems I want to discuss. So let's quickly remove this. Yeah, here now everything kind of gets interesting because now you have constraints to a problem and you are solving this using this genetic algorithm. So again, as before, you have your objective function, lower bound, upper bound. So you don't have any linear constraints. So this is for linear inequalities. These are for linear equality constraints. You don't have any integer valued output. And then, but you have some non-linear constraints in this problem. And that's been written here in this NLCon function. And these are inequality non-linear constraints. The C1, you don't have any, but you have some equality non-linear constraints. So those three are being written here, and then you kind of get this output from this, and you pass this everything you store here in non-linear and you pass this, and everything else you can pass. So you are dealing with 5 variables in this problem, and everything else remains pretty similar to what you have seen in the previous problem or in the PS optimization. So you can run this and you can get your result. Yeah, so these are your results that you get, and again the optimization was terminated based on some sort of a tolerance value. So I think the rest of the problems are also pretty similar. I have some 15 minutes left, okay, and since no one has joined, I don't think so there will be any doubt clearing or anything, so I'll just go through these things only. Okay. So let's move on to the next problem. Yeah, here also the function is different, lower bound and upper bounds are different, and similarly you don't have any this linear constraints or integer outputs. And here also the difference is that you don't have any equality nonlinear constraints, rather you have inequality nonlinear constraints, and when you write it like this implies that these are less than equals to 0 type constraints, so that you have to convert it in that form, and then you have to give the inputs here, and everything else being the same as we have seen before, and you can run this and you can get your solution, which is 3.18 and 1.27. So anyway, so you just need to know what every function does or anything, because you won't be asked to write codes, but you might be asked to like write what will be the output of a block of codes. Yeah, this file has a couple of more problems, I guess. Yeah. Okay, anyway, I think since there is less time, I'll just not run everything. So the next problem also, if you can notice, is that you have just one constraint, which is nonlinear inequality constraint. So that's C will be there, but everything else is C, Q is empty. And this part I have just wrote it down and directly given those as empty here. So you can run that later on as well. Then you have another problem where so let's run this one actually, because this is something interesting. Okay, so you have this function c to the power x1 times this 4x1 square and so on. And now you are generating some sort of a surface plot, suppose, and you are given this points x and y. So this from -5 to 5, you are generating some, say, grid points, and you're storing it in x1, y, and then you're storing everything inside this mesh grid, and then you are evaluating this function at those points z, and then what you are doing, those x, y values you have, and also your function values at those points, and you are drawing this contoured lines. So I'll be showing that to you, and then after that what you are doing, you are having this objective function, Then you are having this non-linear function as before, so you have just one inequality type constraints and the other are empty and everything else has been defined, and you are solving it using GS. So let's run this. Yeah, so this is how your contour plot will look like, and this is your output. So you can also plot this for other problems as well. We just need to create the mesh grid and need to get the function values at those points, and then your contour lines can be like plotted, and contour levels you can give. You can tell whether to show text or not, on or off, those things you can do. Okay, so let's, I think this one has a couple of problems, but let's discuss only one. So you can do some sort of a scatter plot here as well. You can run this later on. And again, you can set some different kind of options to solve this genetic algorithm problem. So these problems are for multi-objective genetic algorithm that we have already seen in this today's class, like NSGA2 and those things have been discussed, and using R. So let's just look at one problem here. So here also what you are doing, you are having two variables, lower bounds and upper bounds are given. Your objective function is written here in this function. So you have two objectives now. So we have seen this similar problems today in R itself. So you have this x1 and then you have this other objective. So you are combining those objectives here and storing it in this objf. And then you are ending this function, so that end keyword corresponds to this function. Then you are writing another function for non-linear constraints that you have. So this is similar to before, but again what you are doing here is that you have to explicitly say pass this as well, this f1 and f2 here and this, and then you are adding those extra c1 and c2 constraints, and then you can pass this everything, this informations using this this GA multi-objective function, and then you are storing everything in RES and F value. So if you run this, yeah, so your optimization was terminated, and this is the kind of plot or the points that you will get from this optimization. So this is again similar to that. This is the other that Pareto optimal front that you were noticing, since there are lesser number of points being used, so that's why you just notice some scattered points here and there. Okay, so that's all about those things that were discussed in the class. So let's quickly discuss this last three problems, I think that's there in the assignment. So let's discuss this one first. So I think it's again pretty similar. The lower bounds, upper bounds are given. A non-linear function is given, and you have to solve it using genetic algorithm, and you're asked what will be the output of it. So again, I have changed some values here and there, so final output might be different. So you need to be careful with that. Anyway, if I run this, yeah, so my final output is stored in this X, which is here it's 3.19 and 1.20, and my fval is 5.68 in this case. So probably you will be asked to give this what is the output of this, but anyway, this is the code and everything is given. So let's just quickly look at the rest of the two. Okay, yeah, so this is for this particle swarm optimization. So again, the function is given, two variable function, lower and upper bounds are defined, and there is this particle swarm optimization, the top option that you are setting, the swarm size and so on. You don't have any constraints and all here, so you can run this, and you get a solution of minus 2.8 and 3. So, and your function value is 0.66 in this case. And the final problem that you have is this one. This is again on particle swarm optimization. Let's quickly check that. So yeah, this LBUB is defined and everything. So you have this objective function, 1 and 2 constraints less than equals to type, and the violation and all have been added, and just passing the particles on through that function, and you get your RES value as 0.006, and this is 0.04, and objective is 1.1. So you get similar problems in the assignment, so you can solve those, but again the codes and everything is given, you can just copy paste and get the answer, not a problem, but you need to know what every function does and so on. Okay, so there is some 5 minutes. I don't think anyone joined. Let's check. Yeah, so no one joined after that. So let's look at the final thing, which is the Excel solver. So let's close this and let's move on to that problem quickly. Alright, so let's look at one problem that was solved in the class itself. So let's do this. So what I have is I think I have already solved this problem. I can set it to say 0 and 0. Yeah. So now what I'm doing here is that I have a function which is this, which is x1 minus 2 whole square plus x2 minus 1 whole square, that I am written, and your x1 and x2 are here. So since you make x1 and x2 as 0 at initialization, you get 4 plus 1, which is 5 at initialization. Then you have two constraints. One is x1 plus x2 minus 2 less than equals to 0, and another one is x1 square minus x2 is less than equals to 0. And then what you can do, you can just run this using the solver that Excel has. So let's quickly go to that. Okay, so where is that solver? Yeah, you go to data and then you go to solver, and if this is not installed already, you can install it using your computer by getting to add-ins, and you can add to Excel add-ins. So I've already given my objective, which is this F7, and I'm minimizing it by changing the variables of this F4 and F5, and then I have added the constraints, which is this F9 less than equals to H9 and so on, F10 less than equals to H10. So everything I have already added, and I probably make unconstrained variables non-negative, so x1 and x2 to be non-negative. And now since I am dealing with this x1 square type constraints here, so that means this is a nonlinear problem. So you have to select this GRG nonlinear solving method to solve this problem. And once you click on solve, then you can get the solution, which is here already. You can notice x1 and x2 change to 1, and your function value is now 1. And yeah, this is some approximation error, but this is essentially a 0 itself. So you have satisfied those two constraints. So that's one problem that was discussed. So I didn't click on OK, so that's why this got changed again, but the actual solution you have seen already. And you can also check it in this answer report. The final value is say 1 and 1 of x, and the final objective value is 1 itself. Okay, so let's quickly again solve this problem, but check one more thing what happens. So when you click on this method to be say simplex, so we have already seen simplex LP can solve for linear programs, but if you click on solve, this linearity conditions required by LP solver are not satisfied because the constraint that you have provided G2 is non-linear. So you will get this error message. So probably we'll get some question related to that as well. Finally, let's look at another problem, one variable optimization problem. I think that was asked in the assignment. So similar problem I'm solving. So let's do this. Let me put this as 0 as starting point, and the function that you are optimizing is say x to the power 4 minus 8 x to the power x square minus 3. So this is the function so that I have written. So when x is 0, you get a minus 3 here. Now suppose you solve it. Let's solve it quickly using solver. So I have already put this f6 as the objective, min problem, f4 is the variable value that you are changing. Suppose I don't make this unconstrained variables non-negative, then I have to use this GRG nonlinear because my constraint is nonlinear here. Now I click on solve. Yeah, solver has converged to the current solution, and current solution of x is 2 and the subjective function is minus 19. You can also check for answer report and click OK. So this will be retained here, and this is your answer report. So original value was given as minus 3, final is minus 19, this is 2 was the final value, and this is also fine. So let's actually, let me just, for the sake of completeness, just complete this, otherwise you might get confused. Yeah, keep solver solution. So now save everything, I can do it. Yeah. So this was the topic of discussion on today. So it is mostly on this optimization using either Excel, MATLAB or Python. So sorry, not Python, R, MATLAB and this Excel. I hope you have understood it through the search lectures and also from this TS session. It would have been nice to have a few people joining in this final class, but that's okay. You can prepare well for the exam. Best of luck for that. And yeah, if you have any more doubts or anything, you can always post your questions in the discussion forum. VTS will be able to answer it. So I think the exam is on 29th, so you still have some 13 days before that, and it will be an online exam that you have to go to the center and take the test too. So probably there won't be any like coding that you have to write, but probably you'll be asked what will be the output of this block of codes and so on, and some problems that you can calculate on your own by hand or by calculator that will be provided on screen. So those type of optimization problems that can be asked, and also the theoretical concepts and all should be clear, and then I think you'll be able to do well in your exams. So with that, I will stop for today. So thank you. So yeah, thank you all, and yeah, best of luck for the exam on 29th.